A multinational enterprise uploads a standard 1,000-word corporate report into their internal artificial intelligence system. They process the document first in English and then translate the exact same semantic meaning into Japanese. This chart shows the severe anomaly in how the system computes data. The English version requires roughly 1,300 processing units to read. The exact same information in Japanese spins rapidly to 4,000 units. The enterprise incurs a 300% cost multiplier simply for switching languages. The language model is not exerting more intelligence or reasoning harder in Japanese. The disparity originates entirely in the underlying mechanism the system uses to ingest text. Specifically, this is a failure of NLP semantic tokenization. Natural language processing is the algorithmic process of segmenting running text into discrete machine-readable units. This mechanism has zero connection to blockchain asset tokenization, which involves digitizing the ownership rights of financial instruments on a distributed ledger. Treating semantic slicing as a minor engineering detail guarantees spiraling infrastructure costs and massive structural inequalities across international deployments. Corporate leadership typically evaluates large language models strictly by their total parameter counts and their reasoning scores on standardized benchmarks. In the generative ecosystem, the NLP token is the foundational unit of economic value, systemic latency, and computational requirement. Chief information officers often assume how an AI reads text is a solved problem. This assumption creates a severe strategic vulnerability. Neural networks do not natively read whole words. They process dense, high-dimensional mathematical vectors that are rigidly mapped to a highly specific, predefined vocabulary. Every enterprise outcome, from the total cost of ownership to the latency of a customer-facing chatbot, is dictated directly by the invisible mechanics of the AI tokenizer. The foundational challenge in computational linguistics is teaching a machine to reliably ingest the infinite variability of global languages, modern slang, and complex mathematical symbols. Mapping every unique word in human history to its own token is too brittle. It cannot handle typographical errors or novel words, and it creates an impossibly large vocabulary for a machine to store. This chart shows an O of n squared mathematical curve, which demonstrates why the opposite extreme, mapping every single character or byte, also fails. A transformer's attention mechanism scales quadratically, meaning long character sequences rapidly exhaust the hardware's memory limits. The enterprise standard is subword tokenization. This approach decomposes rare or unknown words into smaller chunks while keeping common words intact, balancing robust generalization with manageable sequence lengths. The dominant algorithm is byte pair encoding, or BPE. BPE is a data compression algorithm that iteratively merges the most frequently occurring adjacent pairs of characters in a training corpus until it hits a target vocabulary size. BPE relies strictly on frequency. WordPiece, conversely, merges chunks to maximize the statistical likelihood of the training data. SentencePiece takes a different route entirely. It uses probabilistic pruning and treats whitespace as a character, making it highly effective for non-Latin languages that do not use spaces. The specific statistical algorithm chosen to slice human words permanently bakes in the baseline computational efficiency of the entire neural network. When engineers design a model, setting the tokenizer's total vocabulary size is their most consequential hyperparameter decision. Earlier architectures constrained this number to around 32,000 tokens. Today, frontier models utilize massive vocabularies, expanding to 128,000 or even 256,000 distinct tokens. The primary operational advantage of this massive expansion is sequence compression. Complex, multi-syllable corporate idioms map into single tokens, drastically shortening the total length of the mathematical array. Denser tokens accelerate reading comprehension. They allow organizations to pack massive corporate PDFs into a model's fixed context window. The context window is the absolute limit of working memory an AI can evaluate at one single time. But sequence compression triggers a hidden hardware penalty. A massive vocabulary requires engineers to dedicate billions of parameters strictly to the embedding lookup table, consuming vast resources before any logical reasoning even occurs. This parameter footprint directly inflates VRAM usage. VRAM stands for Video Random Access Memory, the specialized hardware memory that limits how much contextual data can physically fit onto a graphics processing unit. Deploying models with massive vocabularies forces an inescapable economic trade-off: Organizations secure rapid text ingestion, but they must procure substantially more expensive GPU clusters to support it. That trade-off compounds when we pivot from the speed of reading data to the cost of generating data. At the conclusion of a step, an autoregressive language model must calculate a probability distribution over its entire vocabulary to predict the next single word. This extreme mathematical constraint at the neural network's final output layer is known as the softmax bottleneck. Upgrading from a 32,000 to 128,000 token vocabulary forces the system to perform 4 times the matrix factorization operations at this final step for every single word it writes. This intense generative effort connects directly to severe degradation in TTFT. TTFT stands for time to first token, the exact latency between a user hitting enter and the chatbot typing its first word. The immense hardware strain of the softmax layer is exactly why cloud providers universally price output tokens up to 5 times higher than input tokens. Massive vocabularies create a critical operational paradox. They highly optimize the ingestion of your corporate data, but they actively degrade the real-time responsiveness of your user applications. Returning to the financial anomaly of our Japanese corporate report, we measure this inefficiency through token fertility. Token fertility is the average number of algorithmic tokens required to represent a single linguistic word. Non-Latin scripts, which often feature complex graphemes clusters like Bengali, suffer from extreme oversegmentation. Standard English-trained tokenizers shatter these complex characters into chaotic, meaningless bytes. This granular fragmentation destroys semantic integrity. Across multilingual benchmarks, as token fertility increases, model accuracy plummets by up to 25 percentage points for low-resource languages. This structural failure extends directly into software engineering. Standard NLP tokenizers fail to accurately align with opcodes and operands when attempting to parse stripped binary assembly code. In molecular biology, processing amino acid sequences requires entirely different architectures. Researchers had to build the atom-level tokenizer, atom disk, to preserve domain boundaries and allow the model to formulate chemical intuition. Similar breakdowns occur in legal reasoning and tax compliance, where nested clauses and highly specialized vernaculars are decimated by tokenizers trained on casual internet text. Deploying generic English-optimized tokenizers into specialized technical domains or global markets degrades the model's intelligence and inherently penalizes international users with a massive language tax. To survive token unit economics, enterprise architectures must actively control how they scale retrieval-augmented generation systems. Retrieval-augmented generation, or RAG, is a framework that fetches external data from a corporate database to ground the AI's responses in specific, verifiable facts. The core structural inefficiency of AI customer service is redundancy. The application resends and recomputes the exact static company rulebook for every new user query. The solution is prompt caching. The infrastructure provider processes the static rules once and temporarily stores the mathematical key-value vectors in distributed memory. Key-value vectors are the specific mathematical tensors within the transformer's attention layers that map relationships between words. Caching solves redundancy. Batch processing solves urgency. By routing non-urgent back-end analytics to asynchronous APIs during off-peak hours, enterprises secure a flat 50% discount on compute costs and heavily reduce networking overhead. A rigorous dual pipeline strategy, synchronous caching for front-end user latency and asynchronous batching for back-end analytics, is the only way to achieve sustainable unit economics. Tokenization also introduces novel cybersecurity risks in open-weight models that traditional network firewalls completely miss, such as tokenizer drift. Tokenizer drift occurs when a configuration file is maliciously compromised. The glitch forces the model to over-segment text. Because billing is tied to volume, this invisible drift inflates compute costs by up to 300% without triggering an alarm. Adversaries also execute token-based denial-of-service attacks. By feeding the AI malicious prompts with highly specific repetitive structures, they force extreme memory allocation during the generation phase, crashing the system at low traffic levels. To navigate these risks, organizations must adopt the value per token, or VPT, framework. This equation demands calculating the concrete economic value generated by a task divided by the specific tokens consumed multiplied by the provider's price. In the automated enterprise, the token is the foundational currency. Organizations that fail to master its mechanics will be structurally outpriced, outmaneuvered, and economically destroyed.